So I want to give a concrete example of regularization and also derive the formula for the gradient of the augmented error when we're doing linear regression. So let me come back to, where am I here? So here is the bias variance trade-off picture. And so that we had this discussion a while ago. You often have hypothesis classes that have an adjustable level of complexity, like regression with polynomial features is a great example. Um, so as you increase the number of polynomial features when you're doing linear regression, um, the variance of the model goes up and the bias goes down, and the error is just bias plus variance plus noise. And so there's some optimal trade-off between the two. So just in the simplistic setting of regression with polynomial features, you can think of this problem as sort of finding the optimal degree of the polynomial transformation that you want to use on the data. So from that point of view, you might wonder why you need regularization, because you do have some control over the complexity of the hypothesis space just with the degree of the polynomial transformation. So regression additionally gives you control over the complexity of the individual hypotheses within the hypothesis class. But in addition to that, sometimes it can happen that when you transform the features of your data set, adding an extra degree to your polynomial can actually give you a huge jump in variance. So let me just, for example, this is the shape of the data set from the concrete data. So there are 1,030 instances and there are 8 features. So look what happens when to the columns as we do a polynomial feature transformation. So when you do a degree 1 polynomial, all you get is a bias column, which increases the number of features by 1. But with degree 2, it already goes up to 45. And with degree 3, it goes up to 165. And then with degree 4, it goes up to 495. So these numbers are going up, I think, quadratically. So they go up quite a bit with each increase in degree. So it might be that the best strategy is to pick something that has, as a hypothesis class, it has a little bit too much variance. But then by applying regularization, you can lower the variance down with only a slight increase in bias, and that might give you your best model. And that's often what happens, what works best in practice. And it doesn't in this data set, and I'll show you that in a second. But let me just show you these pictures that kind of illustrate what's happening with one-dimensional data. So here's 20 data points in a one-dimensional data set, and we're just doing linear regression with polynomial features. So in this picture, the data is being fit with a degree 30 polynomial. A degree 30 polynomial should fit 20 points, but it doesn't, I guess, because of numerical error. So it finds this solution, which is obviously completely overfit. And it has a really great in-sample R2 score of 95. But what this number is the norm of the weight vector. So when we talked about augmented error a second ago, we said that the norm of the weight vector squared would be an additional complexity penalty. And so here the in-sample error plus the complexity penalty will be very high because this is a big weight vector. It's a big vector in terms of magnitude. So here's a solution to the same problem, but regularization has been applied. So in this case, we've tried to fit the data and also minimize the complexity penalty with a certain lambda. And I had to try a few different lambdas to find one that sort of worked the best here. So that's sort of a separate issue. But once we find a good lambda, which is how the complexity penalty is weighted, you can see that it's sort of a better fit. And the in-sample error is lower than the in-sample error of the other curve, but this is obviously going to generalize much better. And you can see here the norm of this weight vector is only 3.67, so it's hugely less. So let's go through this so-called concrete example here. I think I've got this ready for human consumption. So here I'm using from the University of California Irvine Machine Learning Repository the concrete compressive strength data set. So I just read that in, and these are the features of the concrete that get considered if you are curious. And what we're trying to predict is the compressive strength of the concrete from things like the age and the ingredients in the concrete. Okay, so now we load the data, we perform a train test split, and then scale it. So that's pretty standard. And now here's a polynomial model of degree 3. And so you can see that it does okay. Its R2 score on the test set is 0.85, basically. Here's just a regular linear regression. So this is polynomial regression, but with a polynomial of degree 1, it does quite a bit worse. If you try some other polynomial sizes, 2 works okay, 3 works a little bit better, and 4 is too much. So you get great performance in sample, but then really bad performance out of sample. We're going to use regularization to fix that problem, and after we fix it, the degree 4 model plus regularization will actually be the best that you're able to do with just linear regression with polynomial features here. So let's see. So now we're going to do the regularization. This is the formula. I'm going to explain where this comes from and derive it in a separate video. And I've hidden the code on purpose because I want you to implement that. So I hid it in this compiled library here, which I'm going to give to you. So here is polynomial features again with degree 4. But now we do, when we fit the data set and produce W, we do regularization and with a certain lambda. So you just have to experimentally see which lambda works the best. And as you do this, it kind of ruins your test set a little bit for the purposes of determining out of sample error. But you can still use it for model selection. So here I tried basically different orders of magnitude for lambda. So 10 to the -7, -6, -5, -4, etc. So here's what happens. You can just keep your eye on the out of sample error or the test error. So it goes up until it reaches a peak of about 0.87. And this is kind of embarrassing because I think that when we just did degree 3, it was better than 0.87, wasn't it? No, it wasn't. Anyway, let's run all this again. I'm cheating a little bit. I want different numbers than those. Because this is frustrating. Normally it goes up to about 89 or 90 or 0.89 or 90. But in any case, so the best lambda here is about 10 to the -3, and we get this score. So you can compare that to, well, it's much better than the linear model, obviously, and it's even better than the degree 3 unregularized model, and it certainly improved the performance of the degree 4 model, which was overfitting the training set. So I think this is the best you can do with linear regression and polynomial features. But you can, sklearn is able to beat this, but not by much. I mean, it's like 3% better here, roughly 3 or 4% better for random forest. And here's how you do regularized linear regression using the sklearn library if you want to. This kind of regression is called ridge regression. There's also lasso and elastic net, and those are both just linear regression with regularization, but they use different complexity penalties, which we might talk about in a different video. But that's it. That's a good place to stop here. So I will stop this recording.